Alright, this video has the solutions for your 3-7 related rates practice. So first one, this is the kind of problem where we just have an equation given to us here, right? We don't have to make that. So I'm going to go ahead and take the derivative of that. So that looks like, oops, 2y, don't forget your dx dt there, equals dy dt plus then product rule on this, 3, I'm going to take 3x to be the first, so the derivative of the first would be 3 dx dt times the second plus the first times the derivative of the second. If that looks good, and then just plug everything in. So let's see, we're looking for dx dt, so here I got 2x, so that's 6 dx dt is equal to 2 plus 3 times y is -1, that's -3 dx dt plus 3x 9 times dy dt, sorry, which is 2, so that's 18 there. Alright, so let's see, putting all this together, it looks like I have 9 dx dt's, 20, so that's dx dt is 20 over 9. Alright, that's good. Number 2, you're standing on a 10-meter bridge looking down his car. So I think we talked about this one. We did an example like this in class. So same idea here. 10-meter bridge, you're standing up here. That's 10, not changing. And this is 75. I'm going to call that x. And that is changing at 25 meters per second. That's dx dt. And we want to know the angle of the line of sight. So that would be this angle, which is the same as this angle. This is 75 and this is 10, so this up here, we need this later, is the square root of 10 squared plus 75 squared. So I'm going to use the tangent function to set up my relationship. Tangent theta is equal to 10, which is constant, over x, or 10x to the -1. So the derivative of that is secant squared x, theta, d theta dt is equal to -10x to the -2 times dx dt. Right? I just need to plug things in. So d theta dt, when I move secant squared to the other side, it turns into cosine squared. And cosine of this angle is adjacent over hypotenuse, right? Adjacent over hypotenuse. So cosine squared is 75 squared over 10 squared plus 75 squared. Right, that's what happens when I move this over to the other side. You could do that, maybe you did that with your calculator, that's alright. So -10 times x is 75 squared times dx dt is 25. Right. So those cancel out, and looks like I get -250 over 75 squared plus 100. So I've got -0.044 radians per second. Right? Just like an example we did in class. Number 3, if x and y both vary with time and this, so same thing as number 1, So I'm going to take the derivative of that using the product rule. Derivative of the first, dx dt times the second, plus the first times the derivative of the second, dt, is equal to 2y dy dt, and the derivative of 1 is just 0. I'm going to plug stuff in. So I'm looking for dx dt. Looks like I know everything else, so that y is, oh look, it's the same ones as these. Somebody must be cutting and pasting around here. So negative dx dt plus 3 dy dt equals 2 times y, negative 2 times dy dt. So looks like dx dt is equal to 10. So I don't think I messed anything up there. So dx dt is equal to 10. All right. Circular oil spills increasing at a rate of, so this is dA dt, right? That's an area. It's dA dt. How fast is the radius increasing when the radius is 200 feet? So area of a circle, the derivative of that, dA dt, is equal to 2 pi r dr dt. So we want to know how fast is the radius increasing. That's solving for dr dt. So dA dt is 150. 2 pi when the radius is 200. So solving for dr dt, being careful with parentheses in your calculator. I'm just going to put this here so you can see that. That's 150 divided by, and then parentheses here for all the stuff on the bottom. 2 times pi times 200. That's dr dt is equal to 0.119, 3 decimal places. What would the units be? Well, the radius is a linear measurement, which is feet in this problem, per unit of time, which in this problem is minutes. Number 5, the ladder problem. So it looks like the ladder was 12 feet from the ground, so this is 13, this is 12, that means this would be 5. This is constant, this is changing, so there'd be a dy dt in the negative direction, and this is changing, be a dx dt in the positive direction. That's decreasing, that's increasing. The bottom of the ladder is sliding away from the wall at positive 1.5 feet per second. Right, so this is a Pythagorean theorem type problem. I'm going to call these x and y for horizontal and vertical. So my equation is x squared plus y squared equals 13 squared. Taking the derivative of that, 2x dx dt plus 2y dy dt equals 0, and divide through by 2. So that means x dx dt plus y dy dt is equal to 0. So dy dt is equal to 7.5. So negative 0.625. And that would be feet per second. Makes sense that it's negative because that's going to be dropping. All right, number 6. Standing 200 meters away from the launch pad of a rocket that's traveling directly upward at 100 meters per second. How fast is the angle of sight changing when the rocket is at a height of 1,000 meters? Let's see. Kind of like the car problem. We're standing 2,000 meters away, and that's not changing from the base here. This is changing. I'm going to call that y. It's the height of the rocket. That's right now it's 1,000 meters. It's changing, the rocket's going up at 100 meters per second. That's theta, and that's changing too, d theta dt. You're standing 2,000 meters away from the launch pad of a rocket that is traveling directly up. So, okay, so my angle, my equation rather, is going to be the tangent function again. Tangent theta is equal to y variable over 2,000. Derivative of that, secant squared theta, d theta dt, is equal to 1 over 2,000 times dy dt. All right, same as I did in the other problem, I'm going to move that over to the other side where it becomes cosine squared. And for that, I think I would like to know here, that's the value of the hypotenuse. So cosine theta is equal to 2,000 over that squared. That's going to be on the other side when I move that over. So when I square that, that gives me 2,000 squared over 1,000 squared plus 2,000 squared. Adjacent over hypotenuse squared. And that's being multiplied by 1 over 2,000 times dy dt, which is 100. So one of the 2,000s cancels out. I get 2,000 times 100 over 1,000 squared plus 2,000 squared. And that is 0.04. This is going to be radians per, the time unit in this problem is seconds. 0.04 radians per second. Spherical balloon is being inflated at a constant rate of that. So that's dv dt, that's the change in volume. How fast is the radius of the balloon changing when the radius is 8 centimeters? So volume of a sphere, 4/3 pi r cubed. Derivative, dv dt, is equal to 4 pi r squared dr dt. Trying to find dr dt. So, let's see, dv dt is 25 equals 4 pi when the radius is 8 times dr dt. So dr dt is 25 divided by 4 pi times 8 squared. So 0.031 r here is measured in centimeters, and time is being measured in seconds. Okay? Two trucks leave a truck stop at the same time. One headed due north, one headed due east. Exactly 2 hours later. So 2 hours later, that means this would be 120 miles. And this would be 150 miles. How fast is the distance between the two trucks changing? Now, that would be this here. Now that's changing. I'm going to call that y, and I'm going to call that x, just because they look vertical and horizontal. You could call them something else if you want. And then this is changing. dy dt is changing at a rate of 60 miles per hour. And this is changing dx dt at a rate of 75 miles per hour. And then this is whatever that is. So let's see, x squared plus y squared is equal to the hypotenuse squared. Hypotenuse is the square root of 120 squared plus 150 squared. Right? That's just from the Pythagorean theorem. I don't really care what that number is, because when I take the derivative, it's just a number. It's going to be 0. So 2x dx dt plus 2y dy dt equals 0. You can divide through by 2. So x dx dt plus y dy dt. Oh, whoops, hold on a second. That is changing, isn't it? Because one of these, I'm confusing with the latter problem. So this is also changing. That's d squared. It'd be 2d dd dt. The 2 still cancel. So let's see what, I think everything else is good here. We can continue here. That's y dy dt is 75. Hold on. Oh, sorry, that's y. That's 60. It's dy dt equals, and then d is that number that we talked about here. That d is the square root of 120 squared plus 150 squared times dd dt. All right, so I think we can go ahead and get a number there. So 150, this all in parentheses, 150 times 75 plus 120 times 60 all over the square root of 120 squared plus 150 squared. And that's about 96. And last one. This is similar to 6, I think. Space shuttle travels upward at a speed of 500 miles per hour when it reaches an altitude of 5 miles. How fast is the angle of observation changing at this instant for an observer who's 15 miles away from the launch site? So 15 miles away from the launch site. It's at an altitude of 5 miles. This is constant. This is changing, so that's d, I'll call it dy dt. That's like your height, y. And again, we want this sighting angle, which is changing. So tangent theta is equal to the variable y over 15. Derivative, secant squared theta d theta dt is equal to 1/15th dy dt. We're trying to find angle of observation changing. So let's see, d theta dt equal to, if I move this to the other side, it's cosine squared. So let's see, the hypotenuse of this would be the square root of 5 squared plus 15 squared. So cosine of that angle is adjacent over hypotenuse. Cosine squared is this squared over that squared. So that's 15 squared over 5 squared plus 15 squared. That's the cosine squared. Times 1 over 15 times dy dt. Dy dt is 5,000 miles per hour. Right. So 1 of the 15s cancels out. And get that's changing at a rate of 300. And that 300 is, since I did calculus, the angles are measured in radians. And my time here is in hours. And here, we're being asked, that's the correct answer, but I'm being asked to express the answer in degrees per second. So let's see if we can convert that. So 300 radians per hour. So the conversion for radians, 1 radian, or sorry, that's a bad conversion, then the 2 pi radians is 360 degrees. And then from hours to seconds, that 1 hour is 3,600 seconds. So let's see if we can do that. So I got 300 times 360 divided by 2 pi divided by 3,600. 4.77 radians per second. Oh, sorry. Just kidding. Degrees per second. All right. That was fun.